In this video, we're going to go over the Lab 4 vertical jump, the stretch shortening cycle. We're going to take a look at two jumps that we did, or that I did, in addition to the counter movement jump that you analyzed from Lab 2. So this is kind of a continuation of that. We just pulled in everything from the counter movement jump, and we'll take a look at the squat jump and drop jump. The drop jump, I dropped off of a box that was about 0.325 meters tall. It takes about 0.257 seconds for my center of mass to travel down and my body to impact the force plate, my feet to impact the force plate, and when I land, that my center of mass has a impact velocity of about negative 2.52 meters per second. So we'll start off by doing a couple things. Start off with the graph that we need to make of this, so just go ahead and make those highlights there. We'll do insert. We can keep the same graph that we did before. We'll name this appropriately. Drop jump. Force versus time. And then we'll do that also for the squat jump. But before we do it for the squat jump, let's finish up the drop jump. And I'm going to move this up top, just so it's easier to find. Great. So here we are going to do the impulse first. So equals parenthesis, two parentheses, sorry. We need to subtract vertical impulse from body weight on each vertical force from body weight. So we'll take first one minus body weight, and then we're going to add that to previous one, the previous force that occurred, which was 0 in this case. But again, make sure you point to it, don't type in 0, point to it. And then again, subtract by body weight, close parenthesis, so everything in each of these two things will happen first, then you add that sum together and divide by 2. And then we multiply by 0.001. That's just the time difference between each interval of force measurement. So force times time. Whoops. Before I do that, I need to add in dollar signs. There we go. Make sure you have dollar signs for body weight both times. I noticed they were positive rather quick, and it didn't immediately, and it didn't make sense. It does make sense once I get past this point, because 1000 is larger than 778. And we can see from both the graph and from here that force got rather large at the outset. That makes sense. I was crashing down, so to speak, on the force plate when landing. Great. Now we need to do to find center of mass velocity. So that's going to be impulse divided by mass, body mass. And then we add in the previous center of mass velocity from the previous step of interval of measurement. And I need to point again with dollar signs, only this time it's at body mass, before dropping down, like so. So I'm scrolling down, just seeing where it reaches its bottom. It starts becoming positive again. Starts becoming positive right here. Looks like I didn't take those out, so we know one step after it is from negative to positive, that positive step is where the center of mass reaches its lowest. So this is our eccentric to concentric transition right there. Now we need center of mass position. And to do that, we need to do area under the curve of center of mass velocity. Don't need to do anything fancy with this one. We don't need to subtract or add anything to it. Just in the same row, plus the previous row, divide by 2, finding the midpoint, and then multiply that by the time interval between those two measurements. And lastly, I forgot to add in center of mass position. Center of mass position. Great. I'm going to go ahead, control down, that's why I added that in there. It makes it easy to jump to this point. It can verify that this is the lowest. Yes, from here down to here. Sometimes a little hard with how many digits there are. This one's fooling me because the 4 is there, but 4 is more than 2. So with the number of digits it shows, it makes it sometimes a little difficult to see what's going on. And we can see everything auto-populate for kinetic energy, potential energy, and total energy. Let's go ahead and do some calculations here. So net impulse is just the sum of the impulse. I'm going to have to get rid of these last couple because I'm off the plate. I'm going to go down and do that here real quick. Jump back up. So about 418. Takeoff velocity is just the last velocity right before takeoff. Eccentric work. This is going to be the sum. Oh, sorry, not sum. This is going to be the difference between energy at when I make contact minus energy at my center of mass lowest. And then concentric work is when I'm taking off, the last one before I take off, subtracted from the center of mass at its lowest position. So I had to resist in going down 571 joules of work. There's 571 joules of work done on my muscles, so to speak. And then concentric work, I had to then force up from that position, generate a whole bunch of force and work up to move my center of mass up. And it makes sense that it's more than this, otherwise I would not jump up. Okay, so we have eccentric phase time. So how long was that eccentric phase? We use that minus when I first touch the force plate, minus the time when I touch the force plate. Then concentric phase time, so how long was that? That's when I am about to leave the plate, the last measurement before I leave the plate, subtracted from the eccentric to concentric transition. Whoops, accidentally added another in there, another minus sign in there. And then concentric power. This is, if you remember, power is work divided by time, and we must use the correct ones, so concentric work, concentric time. And they are in the correct units, joules per second. Joules per second is watts. Great, just shy of 2200 watts. Great. There are a couple other things you can do while you're here if you want, like energy transfer ratio. Energy transfer ratio, ETR, that's just concentric divided by eccentric work. There's work net, so that's concentric minus eccentric. Instead of dividing, it's minus. And there is the ratio of time that you're spending in them. So how much were you in eccentric versus concentric? okay. So that takes care of this one. You can go ahead and copy stuff in if you want. I'm not going to do it for every single one, but if you want to see how it's done, make sure you just do Control-C, or if you are on, or Command-C on Apple products, you can just do the copy function here. Just come to the correct one. Make sure you do keep text only. That'll keep this formatting the same, not make it look strange. Change the formatting. And you can just keep 2 digits, or 2 decimal places, sorry, 2 decimal places, and go through for that. Great. One interesting highlight that you can see already is there was more concentric work done here. There was more eccentric work done as well for the drop jump. There was more energy in the system because we dropped, or I dropped. The eccentric phase time was rather short, very short, less than half of what it was for the counter-movement jump, although the concentric time's a little bit longer, and it's not that much longer, 0.06 seconds almost. What, 5.56, 0.56. That's very short. But in terms of energy loss and all of that, that makes a difference. That makes a little bit of a difference. So we'll see what that is. If I remember right, if you do the difference between these two to find its network, I think I have it over here. No, I don't have it over here, but let's just take a quick look. Let me zoom in on that so it's a little bit easier for you to see. So 296 versus 292, and that number represents how much work the muscles did, how much work the muscles generated. Not how much ATP they used, but how much work they generated. Which is interesting that they're pretty much the same, a little bit off by about 4 joules, but they're very, very close. So the muscles between the two jumps contributed the same. So the rest comes down to energy transfer and how much energy was available. Energy transfer for this, let's do concentric divided by eccentric, 1.76 versus 1.51. So it looks like the counter movement jump was much better in its energy transfer rate. There was less bleeding of energy going on, although there was more energy in the total system from the drop jump, and that's why it was able to produce a higher takeoff velocity, higher takeoff velocity, higher power overall. So some interesting things in there. It means I kind of had a poor stretch shortening cycle. There was still more stretch shortening cycle going on. It was just a poor turnover, a little bit of a poor turnover. And there could be some ways to optimize that. Maybe I just dropped off a box that was too high. I'm not trained. A lot of things could go wrong with that, but that's for you to ponder and write about below in here. But something to think about. Something kind of interesting that, oh, wow, the muscles generated about the same work between the two. So the rest comes down to the energy in the system, the energy in the tendons, and such. The squat jump, let's zoom in here. For this one, I need to figure out where it starts, because what happened is I bent down to about 110 degrees knee angle. I had someone check. I was holding that position the entire time. And then when the force plate capture was started, I then did a jump from that position. I didn't dip down or anything like that. I just did a jump. Let's take a look at what this day looks like. Okay, so there's a very small dip, and that's probably just my arms moving, from my arms moving. Arms change the center of mass just a little bit because they change the force. So even a small gathering of my arms like that just does that slight dip. But then everything after is just trying to push up, and as you can see beforehand, there's a little bit of a squiggly. It's because my muscles are holding me isometrically in that place. I'm trying not to move. So I can't hold myself perfectly still. There's a little bit more movement than just standing straight up with more or less straight legs. So this tells me I need to start looking for the slight dip at about 1.6, 1.7, somewhere around there in time-wise. So I'm going to go to there, 1.6, 1.7, and look for where it starts going below 778. 1.6 to 1.7, where it falls below falls below 778. Going to use page down. Okay, below 778. Up, and we found it. Let's see where it crosses last. Looks like this is the last crossing before it just starts going slightly down to do the jump. Yeah, we can call that the start. And I'm going to use the drop jump just to copy a couple things over. I don't need center of mass position for this one or the energy stuff. Basically because I did not have a good center of mass estimate for how high my center of mass was. For that, I would need to measure full body motion capture, and didn't want to do it for this. Just wanted to keep it simple. So we can just copy and paste that on over. Impulse and center of mass velocity start at 0. Okay, equals this minus, I'm going to go up to make sure it's weight, not mass. Close parenthesis plus, then we'll point, I forgot a parenthesis, the previous minus body weight again, close parenthesis, divide by 2. I didn't mean to do that. Just make sure you have this minus weight, this minus weight. I'm going to add in those dollar signs, and actually I did not add in the, or not add, but multiply by time. Time difference between those two measurements is 0.001. Okay. And then center of mass velocity. We need to convert impulse to velocity. Impulse divided by mass, and then add in the previous center of mass velocity. And before I do the drop, we'll add in dollar signs. Dollar signs on the mass. I'll get rid of those last two. I forgot to give this a good name. Squat jump. Force versus time. Just a couple things we need. Net impulse. That's just going to be the sum of the impulse. Takeoff velocity, just the last velocity right before takeoff. And then concentric phase time. So that'll be time when we leave the plate, or right before we leave the plate, minus, and in this case, since there is the slightest eccentric, we'll get rid of that eccentric. Where's velocity becoming positive? Okay, right here. So it's a little bit longer than both the countermovement jump and drop jump. Alright, and it produced less takeoff velocity and less impulse. So when we took out that stretch shortening cycle from the countermovement and from the drop jump, we produced less net impulse overall. Weren't able to jump as high, although we can't get from this data, we can't get eccentric work, concentric work, or even just concentric work to figure out how much did the muscles do to look at roughly a good comparison between the muscles of all three jumps. But we have enough here to discuss, enough here to talk about. Anyways, if you have any questions, please feel free to reach out to me. Otherwise, I will see you in the next video.